Hello students, we are into chapter 5 and in the last class we looked at the unit step response of a second order system. So we derived various equations for different conditions like undamped, underdamped, critically damped, overdamped conditions. Okay, so how it looks like? So the input RT, this is RT was something like this. So this is t equal to 0 going like this, and this is 1. The unit step function was the input, okay, and the output will depend on the condition. So if it is okay, what kind of problem we were talking about? We are talking about simple transfer function Ts equal to Cs over Rs equal to omega n square plus divided by s square plus 2 zeta omega n plus omega n square, and three conditions. The first condition, this is how RT looks like. Okay, so the first condition was undamped, and that means zeta equal to 0, and in that case we know that this has to be oscillatory. So output, the Cs, if you want to plot, so this is T and this here is CT basically. Okay, so the long term, the value of that should be about this one. So this is the average value which will be equal to 1. We have seen that the output, the average output will be 1 in the long term, and for the underdamped it will start from here, go like there, like this, and so whatever the solution we got, if you plot it, it will be like this one. Okay, so this is on the damped condition. Number 2, say underdamped. So this is zeta greater than 0 less than 1, and this is this condition. In this condition we have something like this. This is 1, this is CT, and what we see here, it will start from here like this, go up, and eventually it will be settled at 1 like this. Okay, so if you look this kind of thing, that really means this is underdamped simply. If you don't see the fading away, the amplitude is maintained, that's undamped. Okay, here the amplitude is decreasing. So you remember the logarithmic decrement, so that comes from here only. Okay, now number 3 is a critically damped. That is the zeta equal to 1, and in this case this time t, this is 1 like this one. Okay, and CT we are plotting, this will be something like here. It will go and go like this. Okay, something like this. And then number 4, this is overdamped, and in this case zeta greater than 1, and in that case the CT will look like, if this is reference equal to 1, this will look like very slow. Yes, it will takes a lot longer to actually go to the reference value. Okay, so wherever you from this one, basically you can see how the differences. Of course, this one depending on this is underdamped, so this will vary from here to here, yeah. So depending on the value of the zeta, if zeta equal to 1, it will go here, zeta equal to 0 becomes here, in between it will be like that one, yeah. And here also zeta equal to 1, it will be like this one. More zeta it has, more time it requires to reach the reference value, okay. So this you know already from the vibration class basically, yeah. So what is interesting here is basically why we study all those things, so that accordingly we can decide some parameters. So details will come later, but finally what we look at is how the value of zeta plays a role. If zeta equal to 0, you see the input, if you are giving a desired input, right, that's a reference, you want this value. However, the output never stays at that reference value. Reference value is 1. It is oscillating basically. So this is not a good idea. So that means zeta has to be there. If you are designing second order system, that really means you need a zeta, meaning that you need a damper. Yeah. So hence in motorcycle, for example, you have a damper. Yeah. And you don't want a kind of damper which is like critically damped or over damped. You know. So why? Because it may take a longer time to reach the response, right? So it is something like, in terms of motorcycle example, you are going and let us say if there is a pothole, because of that there will be a applied force, right? And then let us say the spring depresses, and it takes long times to go back, you know, so it's not a good idea, because in the meantime there may be some other pothole also, so that time then it will not work, like something like that. So you want a fast response time. So in that case, instead of having overdamped or critically damped, you want something in between where the response is very fast. What you see here, from here it goes here, but you can choose zeta such that it is even faster. You can just settle very soon also. So underdamped condition is that's why very important, and this is widely studied in control system, because what is the advantage? Advantage is response time. Very quickly you can reach the response. There may be a little bit oscillation, but still you will be around there. And hence in motorcycle, for example, yeah, that's a passive vibration control, but it is by a spring mass damper system only, but you have underdamped condition there, so that the response to a pothole is going little bit like this and then settles, goes like this and settles, right? So this kind of action is basically the underdamped only. That may sound familiar to you. So since the underdamped condition is important, underdamped condition, damped response. Yeah. So in that case, as we studied, so if this is the reference where it was the input, this is RT, you can say this one is RT, and our CT was this. So how it does? It goes here, go up, down, and may go like this, and then finally it settles, becomes equal to RT. So this is underdamped how response will look like. Now to characterize it, the system, there are some parameters. Yeah. So those parameters are, this is 1. So first will be the delay time. So half of that, take this one here. Yeah. So time to reach the half of the reference value. So this is called delay time. So TD. So TD, delay time. All those, since you know the equation of this, you can find out, you know, because you know that you put CT equal to 0.5 and you can find out the time which satisfies the conditions, and you can find out the T, corresponding T, right? So okay, so TD you can find out. This is the inverse basically the method where you have to find t when the value is given, and the t when value in the ct is given in terms of sine, for example, right? Sine will be a sine function, and depending on the sine or cosine, both basically, and it will have zeta value, omega n value, and so on. So all those there you put ct equal to 1, and zeta, omega, and all those things are known, and hence you find out time that satisfied that equation, and hence you find out this delay time. Okay, this is called rise time. So from here to here, yeah, so from here to here is tr, right? So this is tr. Again, same thing you can do. So this is the rise time. Okay, then this is the what is known as the peak time. Yeah, so till here, from here to here, so this is the tp. Yeah, tp equal to peak time. This is because here this point it peaks, right? So you can write p like this one. Okay, so this is peak time. Okay, and another parameter is the maximum overshoot. So this one from here to here, this is, you can say mp. Yeah? So mp maximum overshoot. So these are the parameters. Yeah, and this side there is a point where the values are within some percentage. Yeah, so from here to here it could be, or from here to here, like this one. So this will be like within 2%, or since this is 1, so this will be equal to 0.02 or 0.05. So depending on what is the acceptable value. But this one is known as settling time, TS. Yeah, so that tells you that when, so from here to here, right? So from here to here, this is known as TS. So TS equal to settling time. Settling time means when it is close to the reference value, and close means here 2% or 5%. So depending on the system requirement. Yeah, settling time. So time to settle basically. Yeah, time to reach within 2% of the reference point, you call it settling time. Yeah. All these values you can find out. You can find out because you know already CT value is known, which is a function of omega, zeta, right? So since TS is given by omega n square divided by s square plus 2 zeta omega n plus s plus omega n square. So all the function CT will be function of omega, zeta, and of course t will be there. Yeah, so omega n. So the idea is that you can find out, for example, how do you find out delay time if you want to find? So TD, so this we know, we derived yesterday, right? We derived this yesterday. So we say 0.5 equal to function of omega n zeta and t d delay time. 1 equal to f, right? And then we get omega n zeta, and this one is rise time, right? TR. We we take the minimum value. TR will be, if it, of course you will have many solutions, this solution, this solution, this, so you have to take the minimum one. Yeah, so minimum time which satisfy this equation. So similarly TP, so TP will be 1 plus MP. Yeah, so how do you find out? You will take the slope. So that example we have worked also earlier. There was one of the example problems where we had to find what we did. We take the slope here. Yeah, so what we have to do? dc over dt equal to 0. Yeah, so you get two solutions. One will be t equal to 0. Yeah, and then you find out. So TP, this is TP is not equal to 0, and otherwise you can write as minimum TP, right, greater than 0. So TP equal not equal to 0, but the solution, this you will also get, this also you get, all those are the solution of this one, but we are looking for just this one only, the first one. Yeah, so the minimum TP that satisfy this equation. So from there you can find out the peak time. Yeah, once you have this peak time, you can find out the maximum overshoot. Maximum overshoot, how to find out? This is in terms of percentage. Typically you say in percentage. Yeah, so MP, so how do you find out? MP equal to C at t equal to TP minus C at infinity, t equal to infinity, divided by C at infinity, right, multiplied by 100. Yeah, so in percentage you get like that. Okay, and TS you will find out. Let us say our reference is the 0.02. You want to be within 2%. So what will we do? So we will say 0.98 is equal to f omega n zeta and t settling time, and we are interested in the minimum value, minimum TS that satisfies that. Yeah, so otherwise it will be this can also satisfy, probably this can also satisfy, you know, so you have to look at the minimum value where we get the within 2%. Yeah, okay. Sorry guys, it should not be minimum. As you see, all these points will also satisfy. So we are looking for, yeah, we cannot write like this one. That really means is we have to find out 0.98. This function is more than that. So we are looking for this equation. Okay, 0.98. This function is bigger than 0.98. That we have to find out, right? And the minimum TS that satisfy this equation is the settling time. Yeah. So you can also use graph method to do it. You can use MATLAB, Scilab to actually identify it. Scilab, MATLAB may also have the functions to actually find. So all those things are equations, but basically you solve them, you can find it out. But these are the parameters of a second order system, underdamped system. Remember that. Yeah. So that will help basically. So why all these things are important? We will come to know, because you know that it plays a very important role. From there we know that how the system behaves and how close we want, how fast the system, we want the system to follow the reference. All kind of things will depend on these parameters. Yeah. Hence, it's important to know so that we can compare. Okay. Remember that so far we have been studying the response due to a unit step function. However, if you are asked to find out the unit impulse response for a second order system, of course we can do it, right? So all those things I'm leaving on you. And this exercise we have done already for the valuation part. So and for first order system we have done that, right? So we have found out how the first order system responds to unit impulse. Yeah. So Same thing you can apply here and you can do it. Hence, I am leaving this on you. Okay, so we have studies for first order system, second order system. What about the higher order systems? Okay. So let us say there is a system something like this one. So this is GS. Okay. So this is a feed forward transfer function. Okay. So and here we have HS. This is feed back transfer function. This is summing point, plus minus goes like this. Okay, so like this is CS, RS. Okay, just to repeat, basically in case there are still some confusion regarding the feed forward transfer function or open loop transfer function, so I'm going to write it again. So in this case, say feed forward transfer function we will write as TF, right, equal to, in this case will be GS. Then feedback transfer function, let's call it TB. Okay, and that is equal to HS. Open loop transfer function will be, let's call it TO, will be simply TF multiplied by TB. Multiply this and this, you get it, right, equal to GS times HS. And closed loop transfer function, okay, let's call it TC, will be, either you can do the loop analysis like earlier, or you can simply write the TF, which is feed forward transfer function, divided by 1 plus TB, or that would equal to GS over 1 plus, so sorry, not TB, but it will be TO, open loop. Okay, so let's have one more step here. So TF over 1 plus TF times TB, and which is equal to GS over 1 plus GS times HS. Yeah. So this is closed loop transfer function, and this is open loop transfer function. This is open loop. Yeah, and the whole thing is closed loop, right? And error is basically ES. This is ES, ES, and ES is given by simply RS minus CS times HS, right? This is how it is. Yeah. Okay, so this we will follow it, so there should not be any confusion. So this is as per your book also. So this, if I have told anything differently, please consider that now onward we will be doing like this only. Okay, so this is as per your textbook. Okay, okay. So this is how these some terms which are used. Okay. Now, for a like higher order system, so we have closed loop transfer function will be like that only. So we are TS will be like GS over 1 plus GS times HS1. Yeah. So will be 1 plus GS. Okay, so GS. So this is what a transfer function is. So if for higher order system, we can write GS equal to, let us say, PS over QS. Yeah, so where these are polynomials, right? Okay, and then you have HS, let us say call it alpha S divided by beta S. It can be like this. Yeah. Okay, so transfer function TS, how it look like? TS equal to GS, we will have PS over QS divided by 1 plus PS time divided by QS multiplied by alpha S divided by beta S, something like this, right? And hence finally what do you get? You get, so PS divided by, you get QS plus PS alpha S divided by, you get so QS beta S. Okay, so multiply beta S both are numerator and in denominator, we get PS multiplied by beta S divided by QS beta S plus PS alpha S. Okay, so simply what do you get? Actually you get here the polynomial. So this is also polynomial, another polynomial, right? And this is also polynomial. So if these are the ratios of polynomials, of course the final product or the final transfer function is also a polynomial, right? The ratio of polynomials. Okay, now we have to look at what we want basically. Yeah, in what form you can want, you want this to be. So TS, if you are lucky, the system is very simple. In that case, this one, whatever you are getting, we can just write in terms of a summation of, yeah, summation of, it could be AI divided by, and then we have S plus and some value here. Let us say the value is AI, like this one, yeah, or let's call it BI, like this, yeah, where I equal to depending on the how the is equal to n. So depending on the order of this polynomial, you will accordingly will have that. So this is simplest form. Not always we will get like that, but this is the simplest form. Yeah. Okay. Okay. Now if we want to find out the response to unit impulse. Okay, how will you find out? We will be CT equal to L inverse TS, right? That's, yeah, simple response to unit impulse will be some just like this one that we have been doing. And what we will find? We know that AI, we will just sum it up like this one, is equal to AI and inverse Laplace transform of, so I equal to 1 to n ai and s plus bi. So we will get e to the power minus bit. Simply we get that. And we get the answer. Yeah. So what we see here is a multi-degree of freedom system. We will get some answer like that, where bi, this is the simplest form, where bi is a real number. Yeah. Okay. If we had to find out the unit step response, in this case, in that case, what you have to do, Ct is equal to, now you have to multiply it by 1 over s in this case, right? So it will be L inverse of Ts into Rs times Ts. Yeah, and Rs is equal to 1 over s in case of unit step response. So L inverse 1 over s and multiplied by this, I equal to 1 to n ai, right? Sorry. So ai and this s plus bi. So you have to find that. Yeah. So simplification. In fact, you will find that you can have this can be simplified further, okay, and can be made something like this. So from here we are going here. So, or in this case, Ct for the unit step response we are talking about, can find L inverse, and here it will be function 1 over s plus I equal to 1 to n, and there could be something now different, bi, let us say, plus s plus di, something like, yeah. So this we can factorize something like this one, yeah, and then after that if you take the inverse Laplace, and then you can find out the other value. So what we get in this case equal to 1 plus, then you can find out accordingly bi e to the power minus dit, and this will be summation I equal to 1 to n, like that. So meaning that the whole thing, this now can be written something like this one now, and the solution will be like this. Okay, so as I said, this is the simplest form. Okay, so it's not always like that. Okay. Okay, so there could be a little bit complicated as well. So maybe the transfer function maybe look like something like, let us say, is a summation of a combination of something like this. So combination of I equal to 1 to m, where you have ai over s plus bi, and plus could be also like this, I equal to, let me call it z equal to 1 to n, not n, let's say we can, let's call it p, like this. Okay, j equal to 1 to p, and then we may have bi times bj, let's call it, and then omega n, or let's call omega j square over, yeah, and then s square plus 2 zeta j omega j plus omega j square. Yeah. The ratio polynomial could also be like that. Yeah, so that means when we are not able to have all the denominator of this form with this b as a real number. Right? So this is a real number. This is a real number. This is a real numbers. Then in that case we will have two parts. One will have 1 plus bi type of thing, and the other will be the quadratic equation, something like this one. And once we have simplified the original transfer function equal to something like this one, now it becomes very easy to find out the solution, because this kind of things already we know how to deal with it. This is basically second order system, and this is first order system. So what we see is a higher degree, a higher order system becomes a combination of first order system and second order system. We can have like this. Okay, since your course has most of the things since the first order limited to first order, second order system only, so we will not go beyond saying that there could be this also could be not all ratio polynomials can be done this way. There could be a third order system also we have to write. That is true, but let's hope that our problems as far as this course is concerned, we are not getting more difficult than this one. Yeah. So the idea is, in that case, you can, since this is a summation of many first order systems, summation of many second order systems, taking inverse Laplace transform is very easy, because we have done for both of them. Even if we have to find out the response due to the unit step function, we can do it very easily. Yeah. So basically the unit impulse response we can find out as Ct equal to L inverse Ts simply, and whatever the value you can find out, and unit step in response we can find out as Ct equal to L inverse and 1 over S Ts, and like that. Okay, so in this case, or we can use this directly. In this case, we have to again simplify. We'll get this kind of system, 1 plus S plus some summation of first order or second order system, simplify into is equal to summation of first order and the second order system and solve, right, as we have done in the previous case, for example, right? Okay, so this is how you do for a higher degree, the higher order system. In any case, what we see here is a transfer functions. If it is a form of Ps over Qs, let us say the whole transfer function, which is equal to Cs over Rs, then this becomes very important, denominator. Okay, so you can analyze the denominator, and we can find out the some characteristics. Yeah. So for example, as we talked about earlier, like if you want to find out, for example, the response to impulse, unit impulse. And in that case, what do we do? This Qs, we can write Ts equal to a summation of Ai over S plus Bi, I equal to 1 to n, how to find out BI? That really means we can find out BI, find BI by using QS equal to 0, right? And then the solutions are the, so this is the solutions are BI only, right? So basically we can write PS over QS, TS we can write as form of this one, same thing we are writing this one. And how to find out BI? Find BI as QS denominator equal to 0 and solve for S, yeah. And the solutions are S equal to minus, the solutions are S equal to minus BI, right? Okay, find BI by using QS equal to 0. So this is called characteristic equation. Again, transfer function we have PS over QS. So QS, we can write the whole thing as AI divided by S plus BI, summation of that. And where BI we can find out by the characteristic equation, which is equal to denominator equal to 0, QS equal to 0, and you solve for S, and S between solution equal to S equal to minus BI. So this is the solutions. So this BI value is nothing but the minus of the solution what you get. Yeah. So the solution are this one. So here this one is nothing but minus of solution of S for QS equal to 0. So that's what we can write. Yeah. Okay. So now, if you are told to find out the response to unit impulse for this transfer function for this system, how will you find out? We will simply find out CT equal to L inverse RS times TS. RS equal to 1 in that case, unit impulse. So RS equal to 1. We are talking about, say, L inverse TS. And L inverse, we get summation of AI over S plus BI, like this, I equal to 1 to N. And as we know, the solutions are summation I equal to 1 to N, then AI, then e to the power minus BIT is the solution. Okay, so here what we find is the value of this one is important, right? Now, if BI is all BI is greater than 0 to greater than equal to, say, greater than 0, we call it greater than 0, then what happens? If BI greater than 0, you will see all of them will decay. So finally, in long term, C t tends to infinity will be 0. Right? Now, if BI, if all, let's call, if some, if, let's call it, if B, let's call M is equal to 0 and others BI greater than 0, then what do you get? One of them will have this 1, right? So you will find C t tends to infinity equal to simply am, right? You will get am value, because when I equal to m, the bi equal to 0, you put 0 here, this becomes 1, so simply get am value will be there. Okay, so you are giving input, which is the impulse, unit impulse, but output you are getting equal to am. Now, if all or sum, if sum bi less than 0, yeah, then what happens in that case? In that case, you will get bi in this case is negative, and hence the whole thing will be positive. Yeah, and because of that, one of the components will keep on increasing with time. Yeah, so you will get C t tends to infinity equal to infinity, or unbounded, or you call it unstable. Okay, so from here the notion of stability comes into picture. Stability. What we found here, stability really means root. So root of qs equal to 0 is negative. Right? So we call in that case, this system is stable. So let's also understand the stability further, and we solve the characteristic equation qs equal to 0, and we found out this is equal to nothing but s equal to bi, s plus bi, s plus b1, s plus b2, and so on till s plus bn equal to 0. Hence solutions or roots you call, right? Roots equal to minus b1 minus b2 to minus bn. And if all roots negative, means all of b1 b2 bn are positive, then I said system is stable. Yeah. System is stable with respect to what? With respect to at least the impulse response, the impulse input. So there is a system, yeah, and it's a feedback system. Yeah, so this is a feedback system. Like this, and what we are going to do, give a unit impulse, just impulse. Earlier, let us say the state was 0, or some reference, and there we just gave one unit impulse and measured the output. And if these equal to all the roots are negative, then in long term the value becomes 0, right? So we have different components, so all will go like this, that we have studied, right? So all of the roots will go up and go like this. Maybe I equal to 1 will be like this, second will be like this, third will be like this. Yeah, if s equal to 0, one of the roots are 0, then what happens? This remains like this only. That means the output never comes back to the original configuration. S equal to 0, for example, we studied where we said I equal to m, for I equal to m, or rather bm equal to 0. If that is the case, our output value will be c t tends to infinity equal to am, that we just today we did, right? So that really means all the components, if all the other roots are negative, only this root is 0, in that case the long-term value we will be something like go like this one. Yeah. So we have at the end we will find some value am. We started from here. We give some disturbance and output started going like this one. If all roots equal to 0, equal to negative, then we could have seen this kind of trend. So finally this becomes 0, 0, and here this is this value here. So this one is RT, this is CT. So we gave unit impulse here, and here what we see, if all roots are negative, then it will be disturbed, go here, output, and then finally settles to 0. So it starts from 0, finally comes to 0 only. So this is stable. In one of the cases when s equal to 0 you get, in that case, what will you do? What will you get? You get basically not settled like this one, but rather this becomes like this one. So input is like this, and your output becomes like this one. There is a permanent value you get. This never comes back to original position. Hence, this also not stable. So s equal to 0, even if there is one root, s equal to 0, that tells you that is not a stable system. Okay. So let's look at unstable system. Okay, so unstable system. Yeah. So let's say you have just a damper. Yeah, just a damper here, and you are having a force here, Ft input and Xt output. So this is example. So what is the equation? Equation is Ft equal to Cxt, and then Laplace transform, you get Fs equal to Csxs, and transfer function Ts equal to, you get Xs over Fs, right, and which is equal to 1 over Cs. Yeah, so you have 1 over Cs like this. Now let us say impulse response. So unit impulse response, that really means if Ft equal to delta t, that delta function, then what happens? We get Xt is equal to L inverse 1 over Cs equal to 1 over C, and L inverse this one, L inverse 1 over S, but nothing but equal to, we get equal to 1 over just 1. So we get 1 over C times unit step function, right? Or simply equal to 1 over C for t greater than 0. Okay? So basically what do we get from here? It only tells that is if we apply if input is something like this is the input, this t, and this one is here ft. Our output is t here, and here xt is something like this. Value is 1 over c. So that really means it did not come back to its original position, basically. So it displaced from its original position just by one disturbance. Disturbance is here, unit impulse is the disturbance. Just a small disturbance has misplaced this one. It has permanently shifted. X has changed, and hence this tells you this system is not stable. Yeah. Similarly, other example could be this also. You have a mass here, and you are applying Ft. You can also find out. Yeah. So Cm here, and this Xt like this one. This is another example, and you can understand that there is no spring. So little bit of disturbance will misplace it, and this will not come back to original position. So it will be affected by disturbance. And say you have lot of disturbances coming, and say finally it will keep on to like this one, second time it will be like this and like this. You will see that lot of the displacement you see here. So these are the example of unstable systems. And to relate with the root here, transfer function, you see here like this one, and this q s in this case is nothing but this cs, and root will be equal to 0, and hence s equal to 0 is the root. So s equal to 0 root also we see that not good. Yeah. For the second order system, unstable system, second order will be like a spring and mass system, Km, that's it, nothing else. Hence what you get in this case, Ts equal to, this is Ft and Xt equal to Xs over Fs will be given by nothing but 1 over ms square plus k. Yeah, and then what you get is equal to 1 over, so divided by m, so you get 1 over m here, and then you get s square plus omega n square equal to 1 over m, 1. Okay, so just solve the way we solve in control systems. So characteristic equation, so this I may ask in the quiz also, or the continuous evaluation, the assignment. Characteristic equation, q s equal to 0, so that really means s square plus omega n square equal to 0, and s equal to plus minus omega n I, right? I omega n, right? So what we see here is s is complex in this case. And what is the solution? Solution is, if you write, the solution will be the Ct or Xt will be of the form of, as I wrote, right? It should be on the form of, so 1 over m I will take like this one, and then it will be of the form of 1 over m, then e to the power, the first one and second one, right? So minus I omega n t. So we write like this, plus e to the power plus I omega n t. What it tells here is the solution is oscillatory. That really means your input, the input was your input was A like this, right? What you did, you just give disturbance, ft impulse, right? So this is ft, just impulse, right? Unit impulse. And the output you got is like this one, oscillatory. This is sinusoidal. Sinusoidal. And the output, what you get is, will be something like this. This is xt. Again, this tells you that this was the, before this impulse force you applied, the system was resting like this one. The moment you applied here, it started going like this. Like this. Yeah. So hence, the system is not stable. Okay. So what we understand from here is, first thing, S could be real, could be positive, could be negative. S could be imaginary, complex, and could be purely imaginary. Meaning that the characteristic equation Qs equal to 0 can have all kind of solution, right? It can have the complex solution, can have a real solution, can have positive solution, can have negative solution, can have purely imaginary solution. All those solutions is possible. That's what it means. And depending on the solution, depending on whether it is, the value is negative, positive, we can find out whether the system is stable or not. That really means that there is a S-plane, something called S-plane. Okay, and there will be positive here side, you say S. Let us say we denote now S as a complex, where we write S equal to sigma plus I omega. I zeta omega, and typically we write it. Yeah. Okay, and then let's we call just not omega n, just write omega, just omega only. That's it. So sigma plus I omega. So this side is sigma. This is I omega, right? And what we have, this is S plane. We want our root. This is plus side, minus side. For a stable, we want our root to be on the left side. So roots are on the left S plane. Okay, or left half of the S plane. So as long as left half are on the left half or negative half, you can see, as long as we have, for example, if the real number, the S will be here. This is the real roots of Qs equal to 0, and this will be, this is this example, we are purely imaginary. This is purely real. Purely real example I gave. For example, you have a damper basically, and here you are applying a force. Then the roots, then the root is here. Sorry, that is root is here. Otherwise, this is not purely real. This is when s equal to 0. So here this point s equal to 0, which is a real number, is the example of the damper. Purely imaginary, this is the example here. This side will be when your root is, or bi is positive. Bi is negative, meaning that s equal to minus bi, right? So is the root. So s equal to minus of negative number as a positive. So if s is positive, if the root is positive, it will be this side, and hence the value, the ct will be e to the power positive number times t, and hence the value will keep on increasing, hence it will be unstable. So this side it is unstable. Unstable here, unstable here, unstable. Here it is stable, here it is stable. In this case we get 1 on this one, but it is up 1 downside, but on the I omega axis. Okay. So the bottom line is the characteristic equation, the solution of that gives some idea about it. Yeah, and from there we can find out whether the system will be stable or not, and how system will be stable when the roots are on the left hand side of the S plane, and it's unstable if it is on this line, the vertical line, as well as the imaginary line, as well as on the right side of the S plane. So stable, we want the roots to be on the left side. So as long as you make sure that the roots are on the left hand side of the S plane, you will guarantee the stability of the system. And where stability means if there is some disturbance, it comes back to the original position.